You ready to ramp it up? Let's do some challenge problems. So let's take a block and we're going to place it on a frictionless incline. The incline is frictionless because mu equals 0. We'll change this later. The incline has an angle of 36.8 degrees. I chose this specific angle because it makes the nice 3-4-5 ratio. So just like any problem, we'll start by drawing the forces on our cube. So we are on Earth, so we'll draw a force down and we'll label it mg. M is 10 and g is 10. Through this entire problem, I'll put the number and the symbol label so that we'll have both to work with, and we can see cool results with the variables, but also get a number result, which some of you will like more. The other force that we have on it is the force from the incline. So here is the surface. The normal force is always perpendicular to that surface at 90 degrees. We'll label that F subscript N. I've put these two forces on all the other problems for you just to get you started drawing that picture. From projectile motion, you'll realize that when things are at strange angles, we usually break them up, right? So we take anything that's not in this coordinate system of X and Y. If it's not pointed perfectly to the right or perfectly up, then we break it up into pieces, right? Using trig, sine and cosine. But we're not really going to do that in exactly the same way because the block is not moving in the X or Y direction. The block is moving along the ramp. So we're going to tilt our coordinate system. So let's take it and turn it. So it looks like this, which means these are the directions that we're going to keep. And anything that's not in those directions, we're going to break up. Oh wow, Fn is in that direction. That's nice. But mg is not. So what we're going to do is break up mg into something that looks more like this y direction and this x direction. We'll keep this up here for reference. So let's go ahead and follow that perpendicular line down to break up our mg. Let me zoom in here. So we'll have this line down like this. This line is perpendicular to the ramp. Then we'll have a line that is parallel to the ramp. That's in our new coordinate system. The ramp angle down here of 36.8 degrees, let's call it theta, will appear up here in our triangle. That's just because, as you can see, this blue angle, theta, is 90 minus theta, and this whole thing must be 90. So you can just memorize that that angle goes up there, that's no problem. Let's go ahead and break this triangle up into components. Right now you know that the hypotenuse has a value of mg. In numbers, that's 10 times 10 or 100 newtons. This side here is the opposite side. What function relates to the opposite side? Well, that's sine theta. So we're going to say mg sine theta, which if we do that in our calculator, that's 100 sine of 36.8, or basically 37. And we get 60 newtons. Let's follow that same technique for the other part. This is now the adjacent side. So we'll call this mg cosine of the angle theta, or 100 times cosine 37. And that comes out to be 80 newtons. Let's go ahead and apply some Newton's second law now that we have our forces drawn out. So you're going to need two Newton's laws expressions. One for the y direction. Wait a minute. It's weird to call that the y direction. One for this direction. The perpendicular to the ramp direction. The y direction. And let's think to ourselves, does our block have an acceleration in this y direction? Well, the block is going to move this way. It's not going to be going up or down at all. So the acceleration here is just going to be 0. So now this leads us to say, what forces do we fill in under this expression? Just because the right side is 0 doesn't mean it's not worth filling in what forces exist there. So if you look at our diagram, you have the normal force acting up and mg cos theta pushing down. So we're going to write Fn is up and mg cosine theta is down. In numbers, that's Fn minus 80 equals 0. That's nice. It lets us solve for Fn. So Fn in numbers equals 80, or Fn in symbols equals mg cos theta. Okay, cool. Let's go ahead to our other direction, this y direction. I mean, x direction. Now there is an acceleration in that direction, and by x we mean x, right? Parallel to the ramp, the direction that's this way along the ramp, not the real x direction, parallel to the ramp. So if we look at our diagram, it might be that you drew this vector down here, but it really is an mg concept and acts from up here. So we draw it down here so that we know the value of it and that we understand it's part of that triangle, but it just emanates from the mg center point, which is right here. So the only force that we have in the x direction is that in variable form, mg sine theta. That's it, no other forces. In numbers, that would be 60 equals ma. M in this problem is 10. So solving for acceleration, we get it in variable form, m's cancel out, g sine theta. And in numbers, we get 6 meters per second squared. What is really cool about this is a equals g sine theta. Think about what happens as your theta increases. Your ramp is getting steeper and steeper and steeper. And the steepest ramp you can ever have is 90 degrees. And in that case, sine of 90 is 1. And a will equal g times 1. Makes so much sense. Just to reiterate one more time, find Fn and a. Fn is mg cosine theta. That numerically came out to be 80 newtons. On our picture, that part is right here. Acceleration, a, came out to be g sine theta, which mathematically comes out to be 6 meters per second squared. On our diagram, that information came from right here, setting this part equal to ma. You would try the next problem right below it. Then continue on, look at a friction problem, and I'll solve this one in the video. All right, so if you have an incline where there's friction, you're going to start out by drawing that free body diagram the same way you did in the last problem. So you'll have your mg down, so 10 times 9.8. I'm stepping it up and using actually g as 9.8 since we're going to need a calculator from you anyway. Then we're going to go ahead and follow that normal force down to break our mg into components like this. Notice that parallel component is parallel to the ramp. And then you have your normal force perpendicular out of the ramp like this, Fn. Okay, so we're going to write out the component parts. We're going to put this angle right in here. So this side here is the sine side, so we're going to use mg times sine theta, 58.7. And then on this side here, we're going to do mg cosine theta. We get 78.4. The last thing we're going to need is friction. So you're going to have to decide which way the block will slide and oppose the slide. Yeah, the block's going to slide down the ramp. So the friction force is going to be up the ramp like this. Okay, we'll start writing our components out and solving for our individual forces. So let's sum the forces in the y direction. Remember, our axis is tilted, so the y direction is perpendicular to the ramp. Here you see there's normal force and there's that 78.4. And I said they equal 0 because the block is not moving in that direction. All right, onward. Let's sum the forces in the x direction. There's going to be acceleration in that direction. And again, by x, we mean parallel to the ramp. So you have 58.7 pulling you down the ramp. And then you have this friction force pulling you back. Equals m10 times a. Now, you don't know friction. So you're going to have to use that concept that we learned earlier where friction force is mu times the normal. So what are we going to do? We're going to say friction force is mu 0.3 times the normal force, which we just discovered was 78.4. It's not just mg. The normal force is mg cos theta. A scale does not just read the weight. It reads less than the weight. So that number there is going to be different. That gives us a friction force of 23.5 newtons. Okay, so we can go ahead and erase this and put in 23.5. Nice job. Now let's go ahead and solve for A. So 58.7 minus 23.5 gives us about 35 and divide by 10. So we get 3.5 meters per second squared. That's A. Go ahead and try the one below.